Where in the world did the formula sine of alpha plus beta is equal to sine of alpha times cosine of beta plus cosine of alpha times sine of beta? Where in the world did this formula come from? And how on earth would we even show something like this to be true? Well, it's a natural question to ask. Well, maybe sine of alpha plus beta is equal to sine of alpha plus sine of beta. This is a natural first guess for sine of alpha plus beta. And it turns out that this isn't true. Actually, let's say that alpha is equal to beta, which is equal to pi over 2. Let's say that these were alpha and beta. Well, then this side, this is going to be sine of pi, which is equal to 0. And then this side, this is going to be sine of pi over 2 plus sine of pi over 2. And sine of pi over 2 is equal to 1. So this is going to be 1 plus 1, which is equal to 2. So this is not true in general. Of course, if alpha and beta are both equal to 0, then sine of 0 is equal to 0, and then sine of 0 plus sine of 0 is equal to 0. So this equation would be true if alpha and beta were both equal to 0. But in general, it's not true. So how did they come up with this? So one way to go about showing this is to sort of leverage what we know about right triangles and sines and cosines, because remember, sines and cosines just tell us something about the ratios of different sides of a right triangle, right? So check this out. We could draw a right triangle like this, and notice that this angle right here, this is alpha plus beta. And we could sort of play around with these right triangles within this big right triangle to somehow derive the equation for sine of alpha plus beta that I just showed above. But this geometric argument can get a bit messy unless you're clever, although it's a good exercise. And also you have to worry about whether alpha plus beta exceeds 90 degrees. Think about for a minute what would happen with this geometric argument if that were the case. But the way we're going to show it in this video is using complex numbers in Euler's formula. And remember, the complex numbers are just numbers of the following form. They're numbers that look like a plus bi, where a and b are real numbers, and I is equal to the square root of -1. So an example of this would be maybe 2 plus 3i, or pi plus square root of 2i. Those are examples of complex numbers. And Euler's formula says the following. Euler's formula says that e to the I theta is equal to cosine of theta plus I sine of theta. So check this out. Check out what we can do. We can say that cosine of alpha plus beta plus I sine of alpha plus beta, by Euler's formula, this is just equal to e to the I times alpha plus beta. And check this out. This is equal to e to the I times alpha plus I times beta. And remember the exponent law, x to the a plus b is equal to x to the a times x to the b. This is one of the many exponent laws that it's going to help us here. And check this out. Check out what we can do. This e to the I times alpha plus I times beta, this can be rewritten using this exponent law as e to the I times alpha times e to the I times beta. And check this out. Let me get some more room here so I can finish this off. E to the I times alpha times e to the I times beta. This, again, using Euler's formula again, this is equal to cosine of alpha plus I sine of alpha times cosine of beta plus I sine of beta. And check this out, we can just FOIL this. And pause the video and take a minute and FOIL this out and see what we get. So I'm assuming you've had a go at it. So this turns out to be cosine of alpha times cosine of beta minus sine of alpha times sine of beta plus I times cosine of alpha times the sine of beta plus sine of alpha times a cosine of beta. So notice what we've just shown here is we've shown that cosine of alpha plus beta plus I sine of alpha plus beta is equal to this guy right over here. And remember, when two complex numbers are equal, if I say a plus bi is equal to c plus di, then this is the same as saying that a is equal to c and b is equal to d. So in this case, look at what we have. We have cosine of alpha plus beta is equal to this. Let me color code this. Cosine of alpha plus beta is equal to this guy, the part that is not multiplied by I, and then sine of alpha plus beta is equal to this guy, the part that is multiplied by I. So look at this. Not only did we get the angle addition identity for sine of alpha plus beta, but we also got for free the angle addition identity for cosine of alpha plus beta. And you can also, as an exercise, I encourage you to try out the same thing, the same game that we just played with cosine of alpha minus beta plus I sine of alpha minus beta to get the angle subtraction identities.